Okay. Now, in the last video we talked about how we said in this video, we are going to see how Einstein resolved that problem. That every other thing, he tried to see what's going on. Every other thing moved relatively to one another except light. So what's going on? So let's see what he did and what he arrived at, which I can assure you will astonish you, you see. Anyway, now first of all, I would like to say a big thank you to one of the videos I saw on YouTube, which is a video. I'm going to provide the link down there, so just as a mark of appreciation for helping me to understand this. You know, for those of you who know me, I've been away from physics for a while, and now I'm trying to return back to it. My mathematics skills became very blunt, and it's something I think I'm ashamed to say. Anyway, that aside. But the thing is, he helped me to gain a bit more intuitive understanding of this. So I'm going to be providing a link below. You can go to see it. So I'm going to, let's go on. Now, Einstein tried to resolve that problem this way. He started thinking, if the speed of light is the same for everyone, what could it mean? It didn't take very long for him to begin to focus on a component of speed. You know, we define speed as distance moved all over time taken for that distance to be covered, right? Which means the component of speed, those two things that make up speed, are actually distance and time. You see? And the quotient relationship between them, that is, when you divide distance by time, you get speed, which is why we have kilometers per hour. Understand that way? So, he started focusing on these two things. He tried to know what's going on between them. So he started imagining certain scenarios, certain cases, and see what could be the result of it. You know, that's what scientists today call thought experiment. So he tried to sit down and think, if you, listening to me, are with what we call a light clock. A light clock is basically something like, a box with two mirrors inside. And then we have a particle of light, maybe just a point of light like this, bouncing between these two mirrors. So you, in your car, let's say you're sitting down, the car is stationary. You try to measure the time taken for that light, that particle of light, to leave the mirror down here, come up here, and then return back to this place. So the event you're watching is that which has to do with the particle of light moving between these two mirrors. You see? And so you want to, so as it leaves here, goes here and comes back, you hold your stopwatch. And so you measure that time to be T. Now, this is what you see. Now let's imagine again, which Einstein did, that the windows of your car are covered so that you can't know what exactly is going on outside. You don't even know you're in a car, you see. So you have this, and the car begins to move. What does someone sitting outside see? Now, as the car begins to move, you know, those of you who've taken a car before, as you're sitting in a car, imagine that you forget that you're sitting in a car. If you hold, let's say, this piece of chalk, you throw it up, it goes up and it comes down. What you see is that it's happening at the same spot where you're seated. But then again, what would someone who is outside see? He would see something like this. Now, This is you in, oh, sorry. This is you. Still the same you. And let's say the person is outside somewhere here. He's watching you. Now the car begins to move. And as the car moves, let's say the moment at which the car begins to move and when the particle of light starts its journey from this place going up is the same. That moment is the same. So while you who is in a car, as the car begins to move, you see it bounce in one spot. What would this person see? He will see something like this. While you're seeing it bouncing in one spot, he would see, because the car is moving, he'll begin to see the path that particle of light will take will be something like this. Then before it reaches this place, the car has moved to this point. Let's say this is starting point. You see? While you who is still in the car sees it going this way, this person will see it move this way. So when it begins its journey back to the mirror on the ground, the car, now you're still here. You and the car are here when it gets to this place. Now when it gets to this place, you and the car are here. This is still you. You see? So while you see it just move this distance, this guy sees it move this distance. So what is the consequence of all these things? What does it lead to? That's what Einstein tried to resolve. You see? So he looked at these two things here. Now, let's say the car is moving at a speed u meters per second. We don't know what it is. Now, this is where it stopped. Then this guy is having his own stopwatch too, just as you had your stopwatch, and he measured the time to be t. Now this is case A. Let's say TA, this is what your time reads for this same event. This guy sees, this is case B. He measures his own time as this same event you watched happen this way. He saw it happen this way, and he measured his own time to be TB. You understand? Now, the mathematics is very simple, so I'll try to make it as simple as possible. It's simple algebra. A JSS3 student can do this. So, what did he see? Let's say in this case A, you know, Maxwell said the speed of light is the same for everybody. It's not relative, it's just the same. It's unlike the speed of cars, which are relative, which we explained earlier. You can look at the previous videos. Now, in this case A, he said the speed of light is the same. We call it C. Is equal to, now, what is the component of speed? Distance over time, right? Now, what's the distance this thing moved to and fro? It's the distance between here and here is D, which means a round trip would be 2D all over the time you seated in a car. Watch this whole thing take place is TA. Now, for this guy looking here, what would he see? He sees something like this. The time he measures is B. Now, first of all, so let's say this is equation 1. Now, in B, which is this case, this guy watching the same event he watched sees something like this, and his time is what? You know, now, according to Maxwell, the speed of light is the same for you here, and also the same for this guy here. Now, this light is moving here, up and down. You still see it move up and down too, at the same speed. But what exactly is happening here? You can see, so in B, C is still the same, it doesn't change because it has to be the same for everybody. Now, you can see from here, the distance the beam of light, the particle of light moved, is a bit longer than you sitting in the car will see. So let's call this one L, since the distances are not the same. Now, this D is still the same thing here. You understand? And also here. Now, it goes up this way and it still travels down. It's the same length here and here. So they're the same, to denote that they're the same. if you notice here, we have a right angle triangle. And the car, moving at u meters per second, has moved from here to this place. It's covered a physical distance. We don't know the distance, so let's say, let's call this whole distance delta x. So if this whole distance is delta x and this one is cuts this distance into 2, it means here will be x1 and x2. Let's call it, since it cuts it into 2, will be delta x over 2, delta x over 2. It's half. So when you join the whole half together, you get the full length. So now in B, C, which is the speed of light, for these two guys, they must measure the same thing. That's what Maxwell said. Now, why exactly he said that, like I said earlier, is something I've not really, because I have to, it's a different topic. It's electromagnetism. So I have to look into that again. Now, C is equal to, it's 2L now. That's the distance the light covered as this guy measures it. So it's 2L all over. The time he used, his time is, for the sake of clarity, let's use two different things to denote the different times. That's why we have A here and then B here. So we have TB. Let's call this equation 2. Now, how can we find this L? If you look here, we have a right angle triangle. And from Pythagoras' theorem, we know that the square of the hypotenuse is the same thing as the sum of the square of these two sides, the opposite and the adjacent side. So we have d squared plus, what do you call it? This side, remember, we are not considering the entire length. We are considering only the half of the length, which is this divided by 2. This divided by 2. So we have bracket delta x all over 2 squared. Now remember, this is Pythagoras' theorem. So what is our L from here? You take this square over to this side, so it becomes L is equal to the square root of d squared plus delta x all over 2 squared. Now this is what L is. Let's call this equation 3. Now, putting this one in place of this L here in equation 2. So this equation 2 now becomes, we have putting 3 in 2. Now, remember, the reason I'm trying not to miss steps is so that for those of us, like myself, whose math skills are not that strong, skipping steps will make it even more difficult. But actually, it's a simple mathematics, simple algebra. So we have something like this. You put this whole thing here. So now this equation here becomes C is equal to 2. Now what is L? The whole of this. So we have the square root of d squared plus delta x all over 2 squared. Then all over this b, this tb here, this time, the whole thing is TB. So this equation 2 here, as small as it is here, becomes something relatively big. So now, how do we resolve this? We do a cross multiplication. This comes down and this. So this times this will give us CTB is equal to the whole of this now multiplied by this one. Anything multiplied by 1 is that same thing. So we have 2 bracket d squared plus delta x all over 2 squared. You see, we have something like this. Now, let's call this equation, this is 3, so let's call it 4. This d here, can we do something with it? Yes. From here, we can solve for d from equation 1. So we know that from equation 1, C is equal to 2D all over TA. That's the time this guy, U, now measured this. Now, this also implies that now when you do a cross multiplication, we have 2d all over, 2d is equal to c times ta, cta. Divide both side by 2, so we eliminate this and let d stand alone. Now, this implies that d is equal to cta all over 2. Now, let's call this equation 5. So we're going to remove this one and put it in here. Yes, that's what we're going to do. But before we do that, we also have a problem here too. Delta x. Is there a way we can solve for delta x here? Of course, there is a way. Now remember, as this guy is measuring it, he's sitting on the ground. This guy here. This time belongs to him. It doesn't belong to you who is sitting in a car. Your time is this one. And this is what you continue to see, even though the car is moving. Like, in the next time you take, maybe you're going from Yanokbaja to Oshodi, or anywhere you're going to, you sit down in your car, you know, you can imagine this. You see, it brings the world to you in a different way, in a way you've never seen before. That is, if you've not known this before now. You see, it brings it to you that this world we live in, these things we take for granted. We think we know it all. Oh, there are other sides to them. So the next time you sit in your car, imagine these things. While you're in your car seated, imagine you have something like this going up and down. You see it moving in the same spot, and your car is going. The Agbero shouting at the bus stop. He's looking into the car, maybe sitting down. What would he see? He'd be seeing something like this. So this is your own time. You'll be used to measure the event. And then this is the Agbero's time. He watches what's going on. The same thing you carry in your hand. This is what he sees. You see? So now, and these things have profound consequences, which we're going to talk about in the end. You know? So, but here I'm trying to show to you, like many people have shown before in different videos on YouTube and everywhere, that this is what Einstein did and came about what we call time dilation. That what we call time, as soon as you begin to move, you interfere with the flow of it for you. You see? Now this is something so profound that we didn't know before now, before Einstein. Only people called mystics have talked about something close to this, the relativity of space and time. Anyway, but their perspective, like maybe I don't understand it completely, but you can look it up yourself. Now here, back to the same question. Let's see if we can find this delta x. Now, this delta x, as this guy sits outside, you sitting in a car, let's imagine the windows are blinded. You don't have a way to know the car is moving. You'll still be witnessing something like this. But this guy who is outside, seeing the car moving, for him the car has moved from this point to this point when this event took place. So this time is for him. And the car moved relative to him now. You know, every other thing, including cars and everything, they move at relative speed, like we explained earlier. Only light, according to Maxwell, is constant. So the implication of that is what Einstein was trying to understand through these things. So he sees this U. He sees this car moved at U meters per second. So for this guy here, we also know that B moves relative to this person at U meters per second. You know, we are trying to find what is, if this car moves U meters per second, and under this time t, which he observed this event to take place, what will be the distance it has moved? We know that distance, we know that speed is equal to distance over time. Over time. Now, his speed is what? U. That's the speed of this car which you're in, is U. is equal to, what is the distance? Now the distance is delta x. Delta x all over, what is the time? The time is TB, which he saw this thing move here and here. So we have TB here. So can we do a cross multiplication and see if we can find delta x? From here we know that delta x is equal to, do a cross, this multiplied by this is still the same thing. Anything multiplied by 1 is the same. This multiplied by this we get UTB. See? So now we can remove, okay, let's call this equation, this is 5, right? Let's call this one 6. So we are going to put equation 6, 5 and 6 in 4. And let's see what happens next. So we have these two things here. Can we put this 2 into 4? So we can say, putting 5 and 6 in 4. Putting 5 and 6 in 4, we have, this is a CTB, right? Is it CTB? Yeah. Is equal to 2 square root of, what is D now? D is the whole of this. So we are going to have CTA all over 2 squared. Remember, we have to put that square there. Plus, what is delta x? Delta x is UTB. So we have UTB all over 2 squared. We have something like this. Now, let's try to make things simpler. Divide both sides by 2, so as to make here simpler. Divide here. So we have CTB all over 2 is equal to, these two cancel each other out. So we have the square root of CTA all over 2 bracket, squared, plus UTB all over 2 squared. Now, let's open up this bracket. And so we have the square root of C squared TA squared all over 4 plus U squared TB squared all over 2. Now, remember, this square is the same thing. It applies to every single quantity inside. So 2 squared is what? 4. Sorry, let's remove the bracket. Now, let's forget about this. Now we have CTB all over 2. Now, let's forget about this square root sign. Bring this one out and solve it, and let's see. So we have a C squared TA squared all over 4 plus U squared TB squared all over 4. What is the LCM of the 2? We have 4. 4 into 4, 1. 4 into the whole of this. 4 into 4 is 1. 1 times the whole of this. Anything multiplied by 1 is still that same thing. So we have C squared TA squared plus 4 into 4 is still 1. Multiplied by this, the same thing. So we have U squared TB squared. Remember, okay, now we can still bring our square root sign on top of it. The same thing, we forgot. So we temporarily forgot here. Let's bring it back to it. And then it's still the same thing as equal to CTB all over 2. Now, we are going to try to unpack this place. It's what we've been doing all this while. So the next thing we should do is to square both sides. That's take the square root sign to this place. So this one is left without a canopy. So we have, as this one comes in here, it becomes square for everything here. So we have C squared TB squared all over square here, which is 4. Remember, it's very much like, we're still going to come, don't worry, is equal to, now this one has no canopy anymore. It gave up its canopy to these ones, and this one became bigger. So we have c squared ta squared plus u squared tb squared. Now, these are the calculations Einstein did in those days. So remember, as you're going through these things, you know, you're going through the mind of a genius. What was going on through his mind? One of the reasons we see him as the genius that we see him as. So now here, now we have, we're still going to try to make this, it's still a bit complex. So what we're going to do is to remove these ones. So multiply both sides by 4, these ones are going to go away, right? Because when you multiply this one by 4, multiply this one by 4, over 1, over 1. 4 into 4, 4 into 4. So now we have something like this only. So now this whole thing here becomes c squared tb squared is equal to c squared ta squared plus u squared tb squared. Now we have something like this. The next thing we should do is to collect like terms. Now we have tb here, we also have tb here. So we take the whole of this and bring it to the side. So this now becomes c squared tb squared is equal to, excuse me, excuse me, okay. Sorry. Now, we're taking the whole of this and bringing it here. So this plus sign becomes minus, right? So we have u squared tb squared is equal to c squared ta squared. You see? So now that we have something like this, what do? We collect, okay, we bring out a common factor, right? The common term, which is tb squared. So the whole of this now becomes tb squared is equal to, tb squared bracket c squared minus u squared, which is equal to this one here, which you have c, which is c squared ta squared. Now, so you can see the two times which we are comparing are beginning to emerge here already. So the simple thing we should do here is to divide both sides by c squared minus u squared, c squared minus u squared. Now this goes into this, so we have tb squared is equal to c squared ta squared all over c squared minus u squared. Yes. So we'll have something like this. You can see the time, that TB there, is the time for the guy, the Agbero sitting outside. And then the TA there is your time. The time you're measuring this event is your TA. And this person observing that same thing in your hand, he sees something else, and the time he sees that particle of light move between those mirrors is his own TB. So you can see we're beginning to find a relationship between the Agbero's time and your own time. You see, so now we have something like this. What do we do next? You see, we have c squared here, we also have c squared here. We are going to try to find a way to eliminate the speed of light, the square of the speed of light. And how do we do that? You know, see, here, let's bring this one out. Yeah, we have c squared minus u. So now we are going to try something very clever here. Since we have a c square here and we also have a c square here, we're going to have to find a very intelligent way to remove them out. We're not very much interested in that. So one of the ways you can do that is to bring this denominator out here, and let's see if we can represent this same thing in a way that when you still expand the bracket, you're going to have something like this. And how do you do that? You see, when we bring out, although there is no c square here, but there's a clever way we can do it. If we bring out the c square here, and then we divide both sides, these two places, by c squared. So c squared divided c squared will give us 1 minus u squared divided by c squared is still the same thing as u squared all over c squared. So that if you, by the time you want to, how do you say it now, expand this bracket, you're still going to find something like this. C squared times 1 is c squared times u squared all over c squared will give us the c squared. We'll have to cancel each other out, leaving behind just a u squared. So now the whole of this becomes, so here we have tb squared is equal to c squared ta squared all over c squared bracket 1 minus u squared all over c squared, you know, something like this. So now we can eliminate this speed of light, the square of the speed of light. So this goes into this. We have tb squared is equal to ta squared all over 1 minus u squared all over c squared. This is what you have left. But now we are not looking for the square of the time this arc barrel measures and the time you measure sitting on a car. So what we're interested in is we want to know the relationship between the time you measure this same event take place and the time the arc barrel measures the same event take place. You see, because according to Maxwell, the speed of light is constant for everybody. So Einstein said if it is constant for everybody, then something must be giving, something must be changing. And that's the composition of speed itself. What speed is composed of, one of which is time. We're going to look at distance later, but time. So now, you have something like this. This one has so we are going to try to limit this one, break it down a little bit. We'll take this square sign over to this side. So this becomes TB is equal to the square root of T squared, TA squared, all over 1 minus U squared all over C squared. So now, this one will go into this, and that means our TB is equal to, TB is equal to TA all over the square root of 1 minus U squared all over C squared. You see? So this is the relationship between the time the algorithm measures that same event take place, the same event you measure. Let's say this is the light clock you have in your hand in a car, and because the car is moving, you don't know, let's assume you don't know the car is moving, but you still see the event take place at the same spot. It's not moving, no, it's not changing, it's still in your hand at the same spot, while for you the particle of light is moving up and down between these two mirrors. The arc bearer sitting there shouting, "Ah, wawale, wawale." Now, what would he see if he's measuring the same thing? Now, while you have a stopwatch measuring the time taken for the light particle to travel this distance up and down, he's also doing the same thing. Now, what he sees, while you're seeing something like this moving up and down, he doesn't see that, he sees something that goes like this, up and down. Now, the time he measures for this same event to take place is TB. The time you measure is TA. So you can begin to see that the time actually differs by this factor here. And then we have so we now know that therefore TB is the same thing as TA, but with this factor, 1 minus U squared all over C squared. With this same factor. You see? So his time would have been the same as your time, but it's just that it has a little factor multiplied to it. So this means, okay, we are going to talk about that in the next video, the implication of these things. So this is how Einstein was able to come about. You know, all these things he did it in his own mind. And until years later, we were not able to test this in the lab or to physically test it to see if it's actually true. And years later, when it was done, it was confirmed that he was right. So this is why we think of Einstein to be what he is. You know, he was able to sit down and think about scenarios and what would be the outcome, predicted the outcome of it. At a time when that thing he talked about could not be done in the lab, he just sat down and thought, his imagination, and he was correct in the end. So in our next video, we are going to be talking about the implication of this. What does it mean? You see? And I can assure you, it will blow you away. So if you like it, you can check out the next video. Thank you.